So everybody have problem set 5?
Yes.
And you're working on problem set 4. And we will stop class today at 9:30 so that we can do the quiz. Let's go back in time, stop, and then take a quiz.
I'm not going to stay here until 9:30 p.m.
Yes, I didn't say, did I?
Yeah.
I could have lectured all day.
Well, it's a really long question. Well, I guess we'll have to close the year class.
Dr. Harmon just walked in and they both start lecturing at the same time. Using different sets of the board.
That's what we do. Yeah.
You have like a question for both, you just raise both hands.
Okay.
Two cameras.
Now, tell me from your notes, we spent a long time in class on Tuesday deriving the expression for the multiplicity of a monatomic ideal gas. Capital omega. That depends on what quantities. The multiplicity, we're going to specify 3 things. Number of particles, so that'd be capital N. Volume at the position space, that the actual box that the gas is in. And the total energy, which a lot of books will call the internal energy. Now, what is the formula? What did we get for our multiplicity of the monatomic ideal gas? Okay, so there was a function that depended on the number of particles. It isn't that important, not terribly. What's next? What's next? The volume raised to the n power. Total energy raised to the 3n over 2. These two are more important terms than this because the v and the u are raised to powers of n. N is a large number. Therefore, these things raised to that power are very large numbers. Okay? All right, so we're going to spend a good bit of time today using that expression since we expended a lot of effort getting it. Okay? And so, one of the things I want to start with is showing you how sharp this function is, this multiplicity function is peaked about the macro state with the largest multiplicity. There's that fact that the macro state with the largest multiplicity is the most important macro state because this function is going to be a very sharp peak about that macro state, and I want to show you that. Okay? So, I believe we're up to section 7. Ideal gas, sharpness of the multiplicity function. So to have a situation where we would have a sharp peak, we're going to consider 2 interacting ideal gases, much as, for example, to get an interesting result with the Einstein solid, we put 2 of them together and let them exchange energy. So we're going to take 2 ideal gases and we're going to let them exchange energy. We're going to let them come to full equilibrium in all ways, okay? But we are going to allow them to exchange energy between them. Okay? So here's a picture of such a situation. Okay, a schematic picture. We will have a thermally insulated box. So these are the walls here, the insulated walls, the thermally insulating walls of the box. And then I will have some kind of a barrier going down, in this case, through the middle. And I'll have a monatomic ideal gas on this side and a monatomic, same species, let's say, ideal gas on this side. And they will have the same volume. Let's just make this as simple as possible and yet have some interesting physics in it. Same volume, same number of particles, same atoms, right? These are monatomic ideal gases. What can vary for each of them is their total energy. So there'll be an energy for gas A and an energy for gas B, and this container, or this partition between them is thermally conducting, meaning they can exchange energy back and forth between them. So energy can go that way, from A to B, or energy can go from B to A. So what are the things that are fixed? The fixed quantities here. They are the volume of each gas, the number of particles, or atoms, of each gas, and the total energy of the two gases together. That would be UA plus UB. Okay? So I've set up a pretty controlled situation in which really only one thing can be fluctuating: the energy that each gas has, because it can be going back and forth. But the grand total energy, that can't change. Okay? And I contend that when we're in thermal equilibrium, there'll be some macro state with the largest multiplicity. And I want to show you why that's really the only thing you have to worry about, because the multiplicity function is going to be so sharply peaked about that particular macro state. Okay? So I need to start worrying about the total multiplicity of a macro state of the combined system with, let's list the properties that a macro state will have. There'll be some energy for gas A, so use of A, some energy for gas B, use of B. Of course, these aren't independent of each other. Once we specify that gas A has a particular amount of energy, then gas B, its energy is U total minus UA. But I'll list it for now as UB. The volume of gas A is equal to the volume of gas B. We'll just call that V. The number of atoms in gas A is equal to the number of atoms in gas B. We'll just call that N. And remember, U total is UA plus UB. So these are the various properties I can use to describe a macro state. Okay? A macro state of this combined system. And so, what would the total multiplicity function look like? I'm just going to label the quantities it depends on like that. UA, UB, V, and N. Well, remember, because we've seen this before, say with two Einstein solids, the total multiplicity of a two-part system is the product of the multiplicity functions for each one of these. Okay? So, there'll be a multiplicity function for gas A, but that'll just come from this formula up here. That's the multiplicity function for a monatomic ideal gas. And then there'll be, apply that same expression for gas B, and I'll multiply the two results together. Okay? Alright, so that'll be the multiplicity function for gas A for that set of parameters, UA, V, and N, multiplied by the multiplicity function for gas B, which is dependent on those three parameters, UB, V, and N. Okay? And like I said, I'm just going to use the result we derived up there. We've got it twice multiplied together. Okay? So we'll have that function of N twice, right? Because the N is the same for both gases. I'm making this as simple as I can and yet have it still be interesting. Okay? So there's the function f of n will be squared. And there'll be a factor of v to the n for each gas, and I took them to have the same volume, right? So that'll be v to the 2n when I multiply them together. And then the thing that can be different for the two gases is their energy. So there'll be a term u sub a to the 3n over 2, and then a term multiplying that u sub b 3 to the 3n over 2. So that's our first equation in this section. Okay? So far? All right? Now, I keep saying over and over again that for this combined system, there will be one macro state, one set of values for UA and UB, because the V and the N are fixed, aren't doing anything, that will have the largest multiplicity. And that's the most important one. So I might want to know what that multiplicity is. Okay? Any guess on how UA and UB should be related if we're talking about the macro state with the largest multiplicity? In other words, what's the most likely macro state? Because they have equal numbers of particles and equal volume, equal sharing of the energy. Okay? So the macro state with largest multiplicity is UA equal to UB equal to U total over 2. They each equally share the total energy. I'm going to just abbreviate U total, by the way, as U sub T. Okay? Now, if you're saying, okay, I can kind of see why this would be the macro state with the largest multiplicity, where the two gases share the total energy equally, but I'd like to be more certain of that fact, all you're going to do is take this, this equation 1, the total multiplicity for a macro state where UA and UB can be anything, as long as they satisfy this constraint. Okay? Alright? And so therefore write, for example, the UB as U total minus UA, because it's not independent of UA. And then, to get rid of those exponents, take the log of omega total, both sides, and then take the partial with respect to UA, set it equal to 0, and solve for UA. And that'll be the value of UA that corresponds to a maximum in omega total. And you will discover that it is U total over 2. But only because the ends are the same. So you might try to figure out for yourself what the result would be for the macro state with the largest multiplicity if the ends were different. Let's say the V's are the same, but just not to go too crazy. Let's keep the V's the same, but let there be set different ends. Okay? You try that one and see what you get for the values of UA and UB that give you the largest multiplicity in that case. And of course, whatever you get in that case has to reduce to this when NA and NB are equal. That's your sanity check. Okay? But we have NA and NB equal, so that is how the UA and the UB share the total energy to get the largest multiplicity. So I'm going to call this resulting multiplicity omega max. And that's going to correspond to UA and UB both being equal to U total over 2. So I just go to equation 1, right? And I plug in, for each of these, U total over 2. Right? That's what I'm doing now. I go to equation 1, and I plug in that UA and UB are each U total over 2. So then what I end up with is this function of n squared, the volume to the 2n power. And then for each of these, I'll have a U total over 2 to the 3n over 2 power. But now they're the same base. So I can join the base and add the exponents. And so what I end up with is U total over 2 all now to the 3n. That's going to be equation 2, because that's the most important multiplicity. The largest one. Okay? And I'm trying to show you that it's going to be the most important by far. Okay? Alright, and here's where I start to get to where I can show you that. I'm going to ask a question. How likely are what we'll call random fluctuations in energy that take the system away from the most likely macro state. So here's the point. I put these two gases together, and maybe initially their values of UA and UB are not exactly at U total over 2. It depends on what the situation was when I first put them together. But if I let them exchange energy and I wait long enough, they will come to what we call thermal equilibrium. And in this case, since the V's and the N's are equal on both sides, that thermal equilibrium will correspond to each of these having exactly half the total energy. And that's the equilibrium configuration. And that's where it should be then, once it reaches that, if ever I look and see what the energies are. Should be U total over 2 for each. But how likely is it that if I go away and then come back and look again, I'll discover that this one's a little more than U total over 2, and this one's an equal amount less? That certainly wouldn't violate energy conservation. How likely am I to observe that? That's what I'm asking. Okay? So we're going to impose a little fluctuation away from the most likely value. We're going to let the total energy of gas A be the equilibrium value, U total over 2, plus a little bit more. Delta U is just a small amount of energy. It's a positive number, let's say. Okay? So that would be a fluctuation in the energy of gas A above its equilibrium value. Okay? If we do that, then the energy in gas B has to have fluctuated by an equal amount below the equilibrium value. Okay? Now, I'm not going to be too demanding. I'm only going to look for, even a small fluctuation in these energies away from equilibrium. Okay? So I'm not even going to be too demanding. I'm going to say, just give me a little bit. Just a little bit of a fluctuation. Because I'm going to assume that the fluctuation in the energy, delta U, scaled by the equilibrium value of the energy, U total over 2, is very small compared to 1. See, I'm not even being greedy. I'm not even asking for a big fluctuation. Just a little one. Okay? All right, I want to show you how we can use our multiplicity function, equation 1, to figure out how likely this energy configuration is. Okay? All right, so all we got to do is say, well, look, once you specify a value for UA and a value for UB, that's specifying a macro state. Once you specify a macro state, you can get the total multiplicity from equation 1. So let's see what the total multiplicity looks like for this fluctuated macro state. Okay? So I'm just going to plug in my expression right there for UA, U total over 2 plus delta U, and then UB, U total over 2 minus delta U. I'll still have all that stuff out front. I'll have that uninteresting function of n squared. I'll have the volume to the 2n power. Then I will have U total over 2 plus delta U, all to the 3n over 2 power, times U total over 2 minus delta U, all to the 3n over 2 power. Now here what I have to do is I just have to push on the math enough to get an insight, an aha. That may not immediately be obvious where this is going to end up, but you just push now on the math. So for example, what I will do is out of each of these two binomials here, I'm going to factor out a U total over 2. U total over 2 factored out of this, and a U total over 2 factored out of this. Okay? Now when I factor it out, it's still raised to the 3n over 2 power. but then I'll have a factor of u total over 2 to the 3n over 2 from this part, and the same u total over 2 to the 3n over 2 from this part. And when I multiply those two together, I'll have u total over 2 to the 3n. So out front of all this, I'm going to have the function of n squared, v to the 2n. Then I'm going to have a factor of u total over 2 to the 3n from the factoring from each of these binomials. Then I just have to say what's left in these binomials after I factor a u total over 2. Well, in the first binomial, I'll have 1 plus 2 delta u over u total, all to the 3n over 2. And for the second binomial, I'll have 1 minus 2 delta u over u total, all raised to the 3n over 2. Okay? See, I just factored a u total over 2 from each of those binomials. And the first sign that this is going in a useful direction is look at all the prefactors in front of the two binomials in this expression. Namely, all of that right there. Fn squared v to the 2n, u total over 2 to the 3n. Now look at equation 2. What is this quantity here? It's omega max. It's the maximum multiplicity, right? I like the way that's looking. That's a sign to me, keep pushing on this math. It's going in a useful direction. So the total multiplicity for this fluctuated macro state is the maximum multiplicity I can get multiplied by these two very important factors here. These two binomials raised to the powers, you see that, power of 3n over 2. Again, we're getting lots of good practice with bases and exponents and logs and exponentials here. Here what I have with these two binomials is they have the same exponent. Okay? Different bases. So what I can do there is I can multiply the two bases and raise that product to that common exponent. Yes? X to the a times y to the a is x to the y, x times y to the a. Okay? So when I multiply the two bases, now look at that a minute. Multiply the two bases. Notice that this is then just a factored difference of two squares. So when I multiply the two bases, I'm going to get, well, just multiply those out. You're going to get 1 minus 2 delta u over u total quantity squared. And the whole thing is raised to the 3n over 2. Next, I'm going to do something that's very common when working with multiplicities, because multiplicities are very large numbers. So to convert it to just a large number, I'm going to take the logarithm of both sides. Okay? So now we'll take the natural log of both sides. So the natural log of omega total will be. Okay, I'm going to use properties of logarithms. The log of a product is the sum of the logs. So that's the natural logarithm of omega max plus, bring down the exponent, 3n over 2, times the natural logarithm of 1 minus 2 delta u over u total quantity squared. Next, one of our best friends in these courses is the power series expansion for log of 1 plus x when the absolute value of x is small compared to 1. Normally, we only need the first term in this expansion. Occasionally, we'll need the first two. But we'll need the first term here, and that is approximately just x. When x, the absolute value of x, is small compared to 1. So I'm going to apply that here. Okay? Because I do have something that's small compared to 1 here. Now it's minus So think of this as 1 plus that blob, that's the x, which is negative that stuff. So when I apply the power series expansion and take the first term, it's just going to be the negative and the 2 delta U of U total squared for the log. So I've got the log of omega total equals the log of omega max minus, I've got a 3n over 2 out front, and then a 2 delta U over U total squared. Another reason I took the logarithm, besides the fact that this was a very large number and I wanted to reduce it to just a large number, that was one reason to take the logarithm of both sides. The other reason is because I could then use this wonderful power series expansion. Because I've now reduced it to this expression, I've gotten what I want to out of the logarithm, so now I'm going to take the anti-log of both sides. Okay? I erase both sides to e to the power that you see there. So on the left, I'll just e to the log of omega total. That's just omega total. Now technically what I have now is an approximate, right? Because I used the power series expansion. But we're going to see how good it really is. And then I have e to all this stuff. I can break that down into 2 e's multiplied together with these exponents. But then I'll have a term e to the log of omega max. That'll just be omega max. Multiplied by e to all this. Okay? So negative 3n over 2 times 2 delta U over U total squared. And here's the point. I now have an expression, or a mathematical expression, for what this multiplicity function looks like when you plot it versus the only variable we have here. Remember that the energy fluctuation delta U is delta U, go back up there, you will see that it is UA minus U total over 2. Of course it's squared, so it doesn't matter what order those are in. Okay? Now, the point is that so if I want to plot that thing, omega total, I plot it versus UA. That's one way to label the macro states. What's the value of UA? It could be anything from 0, theoretically, up to U total, right? Gas A could have none of the energy of the total system, or gas A could have all of it, or anything in between. Okay? So the point is that this is, notice this function, right? It's e to the minus stuff with the variable squared. And that is one of the most famous functions that physicists deal with, right? This is a Gaussian function of UA. So I can immediately sketch what it's going to look like. I'll sketch it in a way so that we can easily see its shape. It turns out the scale of my sketch will be completely wrong. But it doesn't matter, I'm just going to draw this sketch in a way so that you can see it well. Okay. So let's sketch U total, not U, omega total versus UA. Okay. Okay, so vertical axis, horizontal axis. So UA is the horizontal axis. That can range anything from 0 to U total. Right? Gas A can have none of the energy or all of it, and anything in between. And the most important macro state is exactly at the midpoint between those two extremes at U total over 2. And on this axis, we're going to have omega total. And it's really, I'm just thinking of it as a function of UA, because I'm plotting it versus UA. So when we're at U total over 2, I go up to here, I get some high point, wherever that is. The point is on this axis, that high point is at omega max. And then I know that the shape of this thing is a Gaussian centered about U total over 2. See, remember the delta U is UA minus U total over 2. So it's centered about U total over 2. So that's where the peak is. So it peaks here, and then it's a bell-shaped curve that goes off on either side, like that. Okay? Now, one of the things we want to do is characterize how wide this Gaussian function is, because that's going to tell me how likely macrostates are that deviate away from the high point here. Okay? So I want to know the width. I want to characterize the width of this peak. How are we going to do that with a Gaussian? We could do a full width at half max. That's a very common way to characterize the width of a peak. And there would in principle be absolutely nothing wrong with that. But since it's a Gaussian with e to the minus blob squared, we're going to characterize the width by not going down to the halfway point, which would be omega max over 2, but we'll go down to the point that is omega max times e to the minus 1. 1 over e of omega max. Right? 1 over e, or e to the minus 1 times omega max. E to the minus 1 is about 0.37. So we're saying we're going down to about 37% of omega max instead of 50%. It's arbitrary what you pick, just so long as it's reasonable. Okay? So I'm going to characterize this part here in its equal amount this way. Each of those is a half width. Okay? So each of these is a half width. I get that by taking this Gaussian and just setting the argument equal to 1. Okay? Set the argument of the Gaussian equal to 1. Set the argument of the Gaussian equal to 1. So 3n over 2, I don't need the minus sign, just the positive part of it, times 2 delta u, I'm now going to label it delta u half width, okay? Because that's what this double-headed arrow size, it's going to be the size of that double-headed arrow from side to side, over u total, that's quantity squared must equal 1. And I'm going to solve that for the delta u half width. That will be this width, right here. And I will just tell you what you get when you solve this. You get u total over 2, 1 over the square root of 3n over 2. Okay, so that characterizes this width. So the full width of the peak at this height is twice the half width, right? So that's u total over the square root of 3n over 2. I just multiply the half width by 2. Now what I really want to do to get a sense of the size of that peak, this number by itself is not enough. I have to compare this full width of this peak, basically that distance along the UA axis, with the total distance I have available along the UA axis. How wide is this compared to how much real estate I have? Okay? So what I really want is to take the full width of the peak over the full horizontal scale of the graph. So that's u total over the square root of 3n over 2 in the numerator. And the full scale, the full horizontal scale on the graph is u total. So I see that this goes like 1 over the square root of 3n over 2. That tells me how wide this is, basically as a fraction of this distance. And now we try to get a sense of that scale. And then we will learn how what I drew here, the scale, is completely misleading. Because of this n in the denominator, okay, it's a square root of n, but n, remember, is a large number. So let's say n is, let's say it's 10 to the 24. Well, what do I get when I square root it? What do I get when I take the square root of 10 to the 24? 10 to the 12, right? 10 to the 12, downstairs. So, put upstairs, 10 to the minus 12. Yes? So this is typically going to be like 10 to the minus 12. That's the size of, that's the width of this peak compared to that distance. Again, I've talked about this before. If this is about 1 meter and it's pretty close, then this ought to be a picometer. Right? There's no way you can draw that. And that picture is very misleading. It's a spike right there, yes? Of unimaginable thinness. Okay? So, how much do I have to worry about going away from this container with the boxes and coming back and checking the energies and having observed a fluctuation away from the most likely energy configuration? Not in the age of this universe. Don't have to worry about it. Okay? Now, you can go through a similar kind of argument, since the multiplicity of an ideal gas depends also, say, on the volume of the gas, not just the energy. You could have a slightly different variation of this little discussion that I just made, in which the two gases are in a thermally insulated box, but instead of that partition between them being fixed and thermally conducting, which allowed energy to go back and forth, let's make that partition be movable and thermally insulating, so that no energy goes back and forth between them. Each of their energies is fixed, and so is U total. But their volume can fluctuate, although the total volume is fixed. You see, I could go through a similar argument, and you could make the same kind of a graph. You could work out how omega total depends on the volume of, say, gas A. And what kind of function do you think you would get when you worked out the form for the multiplicity function? You're going to get a Gaussian. Except now, it's going to have a fluctuation in the volume here. VA minus V total over 2. And it turns out you won't have the 3 halves here, yes? Because the volume was not raised to the 3n over 2, but just n. Okay? So you'll just have an n here, not a 3 halves. And then this will be a volume fluctuation over the total volume. But you see how it's analogous to this? And you will come down to the same conclusion, that the width, the full width compared to the full horizontal scale will go like 1 over the square root of n. Again, it will be so sharply peaked that you don't have to worry about any fluctuation in the volume. Okay? Okay. Now, let me just one second, we get a little bit going down the road with that, then we'll take a break. Now we're going to define, for the first time in this class, the concept of entropy. So it should be up to 8. Entropy. I'm just going to give you a definition. It's the definition based on, it's a statistical mechanics definition. You'll get other definitions of entropy if you do just thermodynamics. Okay? But it's really nothing very deep at this point in the statistical mechanics game, It's just based on the fact that multiplicities of our systems are very large numbers. Because they're raised to the power of n something, you know? So very large numbers. And we don't want to deal with very large numbers. We want to bring that down to just say large numbers. Or regular numbers. So take the logarithm of the multiplicity. That's really all the entropy is in statistical mechanics. It's the logarithm of the multiplicity. Then there are just a few details, like, okay, well, we're going to agree to do natural logarithm, log to the base e, because that's nature's choice for bases, for base of the logarithm. And we'll put in a proportionality constant that happens to be Boltzmann's constant for historical reasons. Okay? So, for large systems, so again, we're talking about n of the order of 10 to the 23. The multiplicity goes like some number, I'll just say c, to the n power, where c is just some regular number, which is a very large number. Okay? So the multiplicity is a very large number. We'll take the logarithm, take the log of the multiplicity to get just a large number. Right? We'll go from very large to large. Right? So we're going to take the natural logarithm of the multiplicity. And that really could be all you need if you want to develop statistical mechanics. But like I said, historically, this is multiplied by a proportionality constant, that is Boltzmann's constant, and that would be our definition of entropy, and the symbol is a capital S. Okay? Remember, and note, that from this definition of entropy, natural logarithm of multiplicity is a dimensionless number, log of that is still dimensionless. So all the dimensions of entropy come from whatever the dimensions of Boltzmann's constant are. And in the SI system, remember Boltzmann's constant has units of joule per Kelvin. That's dimensions of energy over temperature. So those are going to be the dimensions of entropy. Energy over temperature. So you can't say that entropy is a kind of energy. It doesn't even have the same dimensions. This is a whole new quantity based on just counting, right, how many configurations the system has for the macrostates that are available to it. Right? That's what the multiplicity is. How many microstates corresponding to the macrostates that are available. That's another way to say that is how many arrangements or how many combinations are there that correspond to the various macrostates. That's what the multiplicity is. So that's really what this entropy is. It's a measure of how many arrangements, how many combinations the system has available to it for the various macrostates. So I'll write that down. So entropy of, let's say it this way, of a macrostate is proportional to the log of the number of ways of arranging the parts of the system. That's a kind of a loose way to describe it, but read the last phrase, number of ways of arranging the parts of a system. as a loose way to describe what we mean by multiplicity. But I say it this way, for one thing, because it's sometimes useful to remember entropy that way. It's proportional to the log of the number of ways the system has for arranging its parts. The more ways it has to arrange its parts, the bigger the multiplicity, the bigger the log of that, the bigger the entropy. Okay?
Is there another definition? Like something?
Well, that's a definition. Okay?
Like in other words, like another interpretation, or just saying that it's the log of
Log of what? Yes. But remember what multiplicity is. A multiplicity is a way to quantify how many ways the system can arrange its parts. Go back and think about the two-state paramagnet, right? If I tell you, I'm going to pick a macro state where out of the n total dipoles, n over 4 are up. Then you could sit down, once I told you what the n was, and you could start listing all the ways it could arrange all its n dipoles to satisfy that constraint. Yeah? That's what multiplicity is. How many different ways to arrange the parts under the given macrostate condition. So this is a wordy way to say what multiplicity is. But I write it that way because a lot of times you'll hear physicists talk about entropy using words like that. Okay? Now sometimes you can get into trouble with just that kind of loose language. And what you've got to always remember is that this is the definition. So to get the entropy right, you've got to make sure you've got calculated the multiplicity correctly. Right? And a lot of times people, it's very easy by the way for this to happen, but people get themselves in trouble because they just use this kind of wordy way to think about entropy, and they think they have then come up with a way to make something that violates the second law of thermodynamics. But when you go back and you look very carefully at the situation they're considering, you discover, well, they didn't really actually sit down and calculate the multiplicity. And so they didn't have a correct understanding in this, whatever this situation was, of what the multiplicity really was. So I do agree that we have to be careful using just this descriptive way. It can be handy, but we also have to be aware that it can trip us up if the descriptive way is a bit oversimplistic. That's the definition of it. Okay? And now we know it's SI units, or joule per Kelvin. All right, so we're going to take our break, I think, and then when we come back, we're going to start looking at properties of entropy, some simple properties of it. And then then we're going to do after that is we're going to calculate the entropy of a monatomic ideal gas. Since we've got the multiplicity function, shouldn't be too hard to figure out what the entropy looks like. And then see what we can learn from that. Okay? All right, so that's what we'll do next.